So the final thing we're going to do is show a particular theorem, which is that for two reactive strategies where the first player is playing P1 and P2 and the second player is playing Q1 and Q2, the probability of cooperating given what the opponent did, that this would be the steady state vector. So this would be the probability of being in each one of our states. So S1, S2, S1 times 1 minus S2, and I'll define S1 and S2 shortly, but just to reassure you, they are simply there for ease of notation. 1 minus S1 and S2, and then finally 1 minus S1 times 1 minus S2. S1 is Q2 R1 plus P2. Again, I'll explain what R1 is shortly. And S2 is P2 R2 plus Q2 divided by 1 minus R1 R2. And R1 is just the difference in the P's, and R2 is just the difference in the Q's. Okay? So if we have two players doing this, then the probability of us being in CC is given by this, the probability of us being in CD is given by that, DC by this, and DD by that, where these are just there for notation. So all these things are functions of P1 and P2, Q1 and Q2, but we just introduced this for notation. The proof of this is not terribly clever. It is simply take this matrix pi and multiply it by the matrix M that we had before, and you'll crunch a lot of numbers, and you'll end up with pi again. Okay, so that's the proof. But what's interesting and valuable is we can write down the long state the long state utilities to both players. So if you recall, our game is A equals in the general form now, A equals RSTP and B equals RTSP. And so we can write down the utility to the first player simply based on those probabilities. So we know they're going to get R, so we're mapping the first letter for the first player, S1, S2 of the time. We know they're going to get, so when we're in CD, the first player gets S, because the other player takes advantage of them. DC, the first player gets the temptation, and then DD, we get that. So we can write down the utility to the first player simply as S1, S2 times R plus S1, 1 minus S2 times S plus 1 minus S1 times S2 times T plus 1 minus S1 times 1 minus S2 times P. And then all we need to do to obtain the utility of the second player is just swap these around. And so that allows us to very easily define a kind of a structure of a player, get our players to play each other, and verify that we get the expected utilities. And that's what I do in the notes using a Python library. But also, furthermore, and this is what a few people started doing, was like, well, if I have this general structure for a player, I can use algorithms to essentially try to maximize this function over my two variables. If I know what my opponent is doing, Q1 and Q2, I can maximize this. And so this was done in various ways, including using genetic algorithms and various other things. That's a general overview of some of the type of work that goes on in the iterated prisoner's dilemma.